Hi students, welcome back to geology. This lecture we are going to talk about igneous rocks, their properties, and how we can identify them. All right, so first things first, igneous rocks come from magma or lava. So this is molten rock that's either found inside the earth or has erupted out of a volcano. The word igneous means fire, so it's pretty fitting that it comes from molten rock or fire. All igneous rocks will start deep in the Earth's crust, and some will solidify underneath in plutons, and some will solidify on the surface out of volcanoes. The two things that we use primarily to identify them are texture and composition. So, texture being what the arrangement of the crystals or grains are, and then the composition is going to be what kind of minerals we're seeing. So, the chemistry that was in the lava that created the different minerals that we see in the rock. Okay, so with texture, we are looking, like I said, at the arrangement of the grains. These could be crystals or they could be other things like fragments of other pieces of rock, and I'll explain what that texture looks like in a bit. So texture is not necessarily how the rock feels. It's going to be what the grains inside of the rock are doing. Are they really big and so you can see them really well? Are they really small? Are they fragmented? All of those sorts of things. And then we have two different types of igneous rocks. So remember, some of them can cool underground and some can cool on the surface. If they cool underground, we call those intrusive igneous rocks. If they cool on the surface, we call those extrusive. So they've exited the crust, so to speak. And so we have extrusive and intrusive, and they give us different textures. And so we'll talk about the different textures within each of those rocks. But a lot of this is controlled by that cooling rate. So how quickly the lava or the magma is cooling is going to give you bigger or smaller crystals. So if you remember with minerals, it takes minerals a long time to grow big. So if the cooling rate is really slow, the crystals can get really big. If the cooling rate is really fast, the crystals can't grow. There's no time, so they crystallize and they stay really small. Okay, so your extrusive igneous rocks, the ones that come out of volcanoes, are going to end up really, really small crystals, and the intrusive are going to give you your big, beautiful crystals. All right, so if you look at these two photographs here, can you see the crystals in either of them? So I'll give you a second to think about it. The big thing is they both have crystals, but can you see them? Okay, so for the one on the left, the black rock, that is basalt, and basalt cools out of a lava on the surface, and it particularly oftentimes has olivine found in conjunction with it, but a lot of times the olivine is so small you can only actually see it in a microscopic view. So in hand specimen, or when you're holding the actual rock, you're not necessarily going to be able to see the crystals. The one on the right, the black and white kind of speckled rock, that is granite, and granite cools underground in a pluton. And so the quartz crystals, which are the kind of clear, glassy crystals there, the white, which is going to be your feldspar crystals, are going to take a lot longer cooling, and so they grow a lot bigger. The black crystals are typically biotite and hornblende in a granite, and so they actually start crystallizing at the later part of the cooling magma. But you can tell that something that formed underground has big crystals, something that formed at the surface has small crystals. Okay, so first we'll look at the intrusive because we really only get one texture type here, a slight variation of that texture type. The big thing here is that we can see all of the crystals in both hand specimen, which is the middle photo, and we can see them in microscopic view, which is the one on the right. So that yellow circle there shows you what the crystals look like in a microscope, and so they're just bigger than what you can see in hand specimen. And so we get very large crystals here, and we typically call this a coarse-grained rock. Okay, so these are our coarse grain where we can see the crystals to the naked eye in hand specimen. Now with our extrusive igneous rocks, these are where in hand specimen we can't necessarily see the actual crystals, but they're there. So if we look in microscope view, which is, again, that circle, that yellow circle there, you can now see the crystals that are in the rock. So you need a high-powered microscope in order to actually see the crystals in a rock that comes out of a volcano, typically. Now, there are some exceptions to that, which I will show you in the next slide. But here we're getting our fine-grained rocks. So our igneous rocks, our typical igneous rocks are going to be fine-grained. Our typical intrusive or plutonic igneous rocks are going to be coarse-grained. Okay, so those are the two big differences in texture. Now we get into some specialized textures like porphyritic. So a porphyritic rock will contain two distinct crystal sizes. And we can have fine-grained porphyritic and we have coarse-grained porphyritic. With fine-grained porphyritic, we have one crystal that is visible and one that is not. So here it's pointing to the visible crystals, which are those black linear crystals. Those are all hornblende crystals in this rock. And then the second one is showing you the gray matrix there, and that is your non-visible, which is making this a fine-grained porphyritic. If they were all visible, it would be considered a coarse-grained porphyritic. So in a coarse-grained porphyritic, all of the crystals are visible, but again, we have two distinct crystal sizes here. So we have small visible crystals that are being pointed to, and then those large visible crystals, which are those pink, larger feldspars in this rock. Okay, so we've got two distinct crystal sizes here. How does that happen? Why are there two different crystal sizes? Why are they so vastly different in sizes from each other? Well, that's because the crystals that are much bigger will start to crystallize much sooner in the magma chamber than the smaller crystals. So for example, with your fine-grained porphyritic texture, you have crystals that have started crystallizing in the magma chamber below the surface. And then once all of the magma is exhumed out of the volcano and onto the surface of the earth, everything else starts to crystallize, so that gray matrix will crystallize around it, which would be the red here. And then those yellow lines would have been those black crystals in the rock. So with a fine-grained porphyritic, we have cooling at different points. So we have one that's cooling inside the earth before the magma has erupted, and then we have one that is crystallizing on the surface when the lava is cooling. With the coarse-grained porphyritic, everything is still solidifying underground or crystallizing underground, but there's just one of the crystal types has started cooling much faster or much sooner than the other one. All right, so looking at glassy textures. So we are moving on from the fine grain and coarse grain kind of designation. We got through porphyritic, which there can be either type. Now we're looking at the rest of the volcanic textures, and the first one here is glassy. So these are all coming out of volcanoes. So this glassy texture happens when the lava is cooling extremely quickly, so almost instantaneously, as soon as it hits kind of the atmosphere. And so there's not any time for any kind of crystals to really form, and we get something quite beautiful like this obsidian here. So this is a black volcanic glass that would have come out of a volcano and has a very smooth texture, as you can see. All right, with vesicular texture, these are rocks that have holes in them, and basically those holes are where gas used to be trapped in the lava. And so as lava cools, that gas starts to escape. And because that gas was taking up space in the lava, it also remains in the rock. So those spaces are these holes. And so sometimes people will use a vesicular textured rock like pumice to scrub their feet, which is why there's a photo of that there, because it is pretty effective at getting dead skin off, because it is technically volcanic glass as well. So it's the same as the obsidian I just showed you, but in very small particles with lots of holes in it. Okay, so this vesicular texture creates things like pumice, and we use it to scrub our feet, maybe. Or maybe use it to scrub your toilet. People use it for that too. All right, and then our last one here is a pyroclastic texture. And pyro meaning fire, clastic meaning fragments of things kind of stuck together, so clasts. And so what we see here is during an eruption, if there's a lot of ash present during the eruption, that ash will coalesce after the eruption and create a rock. Now, this can be all ash, or it can be ash and a bunch of fragments of rocks and maybe some crystals that were trying to form. And so, depending on whether you have all ash or the rock has some rock fragments in it, it's going to be called something different. We have a breccia has ash holding together a bunch of rock fragments and some tiny crystals. And then the tuff is almost entirely ash. Okay, so just depending on the amount of ash present and the lack or presence of rock fragments, it's going to distinguish which of these two rocks you're looking at. And so again, this is a pyroclastic texture. This is probably one of the harder textures for people to really grasp because sometimes it just kind of looks like a mesh of things. So the breccia, if you've ever looked at concrete, kind of looks like concrete, but it's not. So you just kind of have to get a feel for it as you work through the rocks. Okay, so your first job is to try to figure out what each of these rocks' texture are. So you'll do this in lab as well, but I want you to look at each of the images and see if you can decide what type of texture it has. I won't go over them in this lecture, but I want you to try, and then you'll answer the question and see if you can figure it out. Some of them have already kind of been talked about, so it shouldn't be too difficult for you. Just keep in mind they are kind of grouped, so to make it easier, since they are photographs and not actual samples in your hand. All right, so we talked a little bit about Bowen's reaction series in the last lecture, but we're going to kind of continue it here. Oops, there's a little typo there which says add more text. Don't worry about that. So Bowen's reaction series shows us how crystals are crystallizing out of a magma or a lava and at what temperature typically. So in the early 20th century, geologists studied igneous rocks pretty intently and are trying to categorize the minerals that they were looking at and the rocks they were looking at, the chemistry that they saw in those rocks, and trying to decipher trends. And that's basically what this reaction series does, is it shows us trends of crystallization in particular magmas. And we can look at those magmas and say, okay, well, we think that kind of falls here on this scale, and then make inferences about the volcano's future, past, and what's happening currently. Okay, so here is the Bowen's reaction series in a real small graphic. So we have olivine at the top, which is cooling at the highest temperature lavas. So it will cool at a very high temperature because it cools quickly. And so it creates really small crystals. And then down there at the bottom, which is cut off, oh my goodness, I apologize. This is cut off here, but it says quartz down here at the bottom. And the quartz will crystallize at a much lower temperature, closer to about 600 degrees Celsius. I'll fix it when I actually PDF it for you. So at the lowest temperature, around 600 degrees Celsius, that's when quartz is going to crystallize. And that's going to give us our felsic or granitic rocks. And so depending on what crystals we're seeing in our rocks, we can actually figure out what type of igneous rock we might see. So are we looking at a very high magnesium and iron, which is going to give us our olivine, very dark colored rocks? Or are we seeing a lot of silica and oxygen, which is going to give us our granitic, our felsic, really light colored rocks? Okay, and we use this to kind of infer what the conditions of the magma or the pluton was at the time of eruption or solidification. All right, so magma and lava contain three basic components. We have melts, we have solids, and we have volatiles. Okay, so the melts are the ions from the minerals that have liquefied. So it's all of the liquid minerals. The solids are any minerals that have started to crystallize and are just floating around. So that would be like in your porphyritic texture. Those are the crystals that are just kind of floating around. in that liquid melt, that magma or lava, whatever point it is in its journey. And those are all crystallized minerals. Your volatiles are any kind of gas components. So those are going to create your pumice or your vesicular texture, right? And so if you have a high level of gas or volatiles in the lava, it is going to make it more explosive, and it is going to create more of that vesicular texture. Okay, so this could include water vapor, carbon dioxide, sulfur, chlorine. There's lots of different gases that can be. Those are the typical components that we would see in a magma. Right, so as you go down into the earth, there is something called the geothermal gradient, and so this is the rate at which temperature is increasing at depth. Depending on where you are on Earth, the geothermal gradient is different because there are different conditions, right? So when we talked about plate tectonics, there's a lot of things going on with plate tectonics, and depending on where the rocks are being formed, at which type of plate boundary, you're going to see a different geothermal gradient where things can start to melt sooner than a typical geotherm, or they could melt a lot later than a typical geotherm. And that is just with the addition of water vapor, with the addition of extra hot material. All of those things will kind of impact where things start to melt. So looking at some of the different plate boundaries. So in a normal situation, we have the geotherm that dips in this pretty steady orientation until it gets about 150 kilometers deep and it starts to curve a bit. But in a mid-ocean ridge, we see that rocks start to melt a lot closer to the surface. And that's because two plates are pulling apart and magma is coming up from the mantle. So things are a lot hotter. So you can kind of see that geotherm bending there. That 1200 degrees Celsius is coming closer to the surface. With a hot spot, it also bends a little bit earlier than in a normal situation. So the geotherm does bend a little bit up depending on where that plume is sitting in the crust. And then again, with an island arc or a subduction zone, we also see a bend in our solidus. So that is our solid rocks actually starting to melt sooner, and that is shifted over because of the addition of water into the mantle. So when water or hydrolyzed rocks that have a lot more water in them on the subducting oceanic slab, when that enters the mantle, that allows for a lot more vaporization, and the magma can upwell a lot quicker. So that's going to cause things to melt a lot closer to the surface. Okay, so this is the geothermal gradient and the different situations depending on where you are in the different plate boundaries that are available on Earth. All right, then looking at some decompression melting. So magma is created at mid-ocean ridge, and it's formed from decompression melting, which is when we have strong convective currents coming to the surface, and it's slowly flowing beneath the lithosphere. So here we have a poor heat conductor. The temperature remains about the same. So things are pretty much melted all the time until they come to the surface and they start to solidify. So where the convective currents are causing mantle material to rise, the pressure is decreasing, which causes melting point to drop. And that's how the rocks are melting there. Then we have flux melting, which is also called fluid-induced melting. This occurs at the island arcs or where we have subduction zones when those volatile gases or those water vapor gases are entering the mantle. And there, like I said, we have water vapor interacting with mantle material, and it's volatilizing everything and creating a lower melting point for that magma to come up. And something that's melted is going to be less dense and hot, and it's going to start to rise. And so that's the flux melting. And in some of these rocks, we start to see some partial melting. And so partial melting will start when rocks start to get so deep as they're buried some of the minerals start to melt, but not all of them. And so we'll revisit this when we look at metamorphic rocks. But what's happening here are some of the crystals are not staying completely solid, and they are starting to melt within a solid rock. And so it's kind of like molding a Laffy Taffy, and part of the Laffy Taffy is starting to melt. And then you re-solidify it and it comes to the surface, right? And so that's kind of what we're seeing here with partial melting. And this will come in conjunction with burial. So the rocks are getting deeper and deeper in the crust by tectonics, or it can come from the presence of some sort of heat source like other magma coming up and melting existing rock that's there. Okay, with fractional crystallization, this has to do with the magma and the way the crystals are crystallizing out of that magma. So in general, we see an increase in silica content from time 0 to full crystallization. And so olivine is a mafic mineral. We already talked about that. So it's high in magnesium and iron. And it is a lower percentage of silica. So that means that olivine is going to crystallize first at the bottom, and it's going to leave the melt. So all that magnesium and iron is no longer going to be in the magma anymore because it's crystallized out as an olivine. And so then from there, we start to see more and more silica content. So in a volcanic eruption, what tends to happen with some of these volcanoes is they might start off very high in magnesium and iron. So they have a lot of mafic rocks coming to the surface and solidifying. And then over time, they turn into more what we call silicic or felsic volcanoes, because those tend to stay in the melt longer and they crystallize later. And so you might not see the same type of rock come out of a volcano every single time. It might be kind of a series of different types as the magma is evacuating the chamber. And when these rocks start to erode, which we'll talk about sedimentary rocks next, but when they start to erode, they are going to exhibit the same features they did as a rock, right? So if you have basalt, which is a black rock, and it weathers into some sand, it should give you black sand, right? And as I mentioned before, olivine is often found with basalt, and olivine is olive green. It is a green colored crystal. And so in Hawaii, you have the black sand beaches, and you also have some green sand beaches in Hawaii. This one's on the Big Island of Hawaii. It is beautiful, by the way. If you've never seen green sand, I highly recommend trying to get to this beach. But this is green sand, which is created from the olivine that's found with the basalt that is erupted out of Kilauea, Mauna Loa, Mauna Kea. But if you go to some of the real touristy areas on the Hawaiian Islands, there are some white sand beaches, particularly Waikiki Beach on Oahu. And it's very interesting to see why there's such a stretch of white sand. Where did it come from? It was imported from California. So in the 20s and 30s, when tourist population in Hawaii was kind of booming, a lot of people were worried that the black sand was going to deter tourists because everybody loved California beaches, and California beaches were white. So they imported a ton of white sand from Manhattan Beach, and it was kind of devastating because it starved Manhattan Beach for a very long time. And when the EPA was created in the 1970s, they had to completely stop. And now, where do they get their sand? I have no idea. But it continues to be white from what I can tell. So they imported a lot of sand. And when you remove sand from a beach, it really hurts that habitat. It hurts the coastline. So it really was not a sustainable thing to be doing, especially to an area that people live really close to the beach or close to the coastline. And yeah, just for vacation purposes. All right, so igneous rocks. We have these textures. We have coarse grain, fine grain, glassy, vesicular, pyroclastic, and then our porphyritic can be coarse or fine. The magma is generating these rocks, and it can be generated from various melting forms with decompression melting, flux melting, or partial melting. We know that the geothermal gradient will demonstrate the temperature at depth, and depending on the plate boundary it is located at, you're going to see a shift in that geothermal gradient. And then as rocks break down to sand, they will always show their trace or their parent rock's features. All right, so in the next video, you will move on to sedimentary rocks, and I will see you guys there. Bye.